We'll further look at more properties of these set of formula in 7.4. Okay, up to here, any questions? All right, then we'll move to 7.4. And again, you pay attention to the fact that they are not the same, the two set. Now the first property, you look at the refracted rate, the way refracted back. So you're basically comparing this with that one. So case 1 and case 2, obviously they are not the same. And generally, there'll be the one of them is actually larger than, in general, larger than, right? And that, that I think actually has a big deal. Oh, no, it doesn't have. And I think it's just pointed that out. If you actually plot the function, plot this function as a function of I for given n and n prime, obviously it's easier to set mu equals to mu prime. So set this to 1, and in this discussion of this property is easier to look at that setting mu equals to mu prime, which is usually the case, because both mu and mu prime should be very close to mu's of 0, right? For most medium. Yeah, so in that case, you can actually plot this function as a function of R, and show that one of them is much larger than the other. And in particular, for case 2, for the case that the electric field is on the plane of instance, there's an angle such that the refracted wave is exactly 0, or E0 double prime is exactly 0. Right, so that is called the Brewster angle, and that is you can now divide that with the assumption mu equals mu. For case 2, so you get E0 double pi is just look at the numerator. The denominator doesn't matter because we change the sign, and we'll show that the numerator goes to 0. The numerator is E0 double pi is 0 when this is 0. So n pi square is I equals to n square root function n pi square minus n square sine I. Well, if these two terms are the same, then we cancel the two terms, and that becomes 0, right? And now we can look at what we can try to solve for I, in this case, for this equation. And the first thing to do is you may square that one, so n pi 4 plus 1 square I equals n square times n pi square minus n square sine I. Okay, and now the next step would be change that to 1 minus sine square. Right? Just that's just the trigonometric identity. Now you group the term of sine square I, the sine I, and then group it like So move this to the other side. This is minus, this is move to the other side, becomes plus n to the 4th power minus n pi to the 4th power equals to equals to, so move this to the other side and this to the other side. So you have n square, n pi square. This move to the other side. So it's n pi 4. So n pi square, n square minus n pi square. Wait. It looks complicated, but hopefully we can simplify later. And this is n pi square, n square minus n pi square divided by this one. This is the n fourth minus n pi 4. But we can simplify that because n fourth is n square square. So this is a square minus another square. So it's n square plus n pi square. N square minus n pi square. Right? So this is just this one. And you have this factor, n square minus n pi square, so this two cancel. Okay? Right? That, so that is actually a formula, but there's an even simpler formula by realizing this is sine, and this is n pi over n square over n pi squares. So this looks like a triangle. If you just look at draw a right triangle. Right. Sine is so if this is n pi, this is square root n pi square plus n square. This is I. That is sine, right? And n pi, because this is square, you take the square root. This is n pi and divide it by square root of this one, and that would give you the I. That would give you the sine, right? You remember the trigonometry. And so what is this one? Then what is the name? N. N, just n, right? Because this is already square root. This is n, right? This that's just the property of the right triangle. This is just a going through it. So, and look at the triangles here, obviously. An easier formula, tangent I n pi over n. Tangent I is n pi over n. And in this case, we give it a name. This is we call it the Brewster angle. Or I sub b would be a arctangent n pi over n is 7.43. Okay, so that's this angle will make this the numerator goes to 0, or the refracted wave is totally 0, and so that's for case 2. And you can try to do the same thing for Brewster, or maybe BREW. WT Brewster's angle. Yeah, we haven't heard of this before. Yeah, this is okay. Anyway, so that is actually a topic that in undergraduate optics, if you have taken it. All right, so and I was saying that for case 1, you cannot do the same thing. When you try to do that, it will not give you a solution. Right. You cannot find a solution. That actually, I think you can also show that for case 1, that is always positive. So there's always some power. It does not go to 0 for the whole I. Right. whether there's a good way to look at it, but you just need to work on the property. I mean, look at the equation. So, I mean, I can set this to 1. When I goes to 0, this will be n pi. So n minus n pi, right? When I goes to pi for 2, this becomes 1 is n pi squared minus n squared, and obviously we are talking about I mean that is n pi is greater than n in this case. So and so that is n. So this is n and minus something that is n pi squared minus n squared. But so that with this one it will be smaller than this one, and so over the whole range actually is that this condition will not. I mean, it won't satisfy that the same situation, and that the refracted wave is 0. All right, but anyway, that's that you can try to figure that. But for the second case, it's this angle, and obviously for any n and n pi that you always have this angle. This is a tangent. So whether it's greater than 1 or smaller than 1 doesn't matter. You always have an angle that the refracted wave for this situation is exactly 0. And there's a physical understanding for that also. So in this angle, you can actually apply the Snell's law to see that. Basically, now if assuming you have a Brewster angle, you have an I here, and then you have R, and if this is I sub B, this is R, right? And this electric field will be pointing in this direction, right? And the idea is that R plus IB will be pi for T, will be a right angle. And so this would be a right angle. So this refracted wave will be along the same direction as this electric field direction, right? And to show that is actually using the Snell's law. You can try to see that the Snell's law is so this is n prime, this is right. So n sine I B is n prime sine I. Oh, not sine R. Yeah, the Snell's law. Okay, and now we can also write the easiest way to do that is so we can use that the property that sine is just tangent I b times cosine plus b. Right, that's just that's the definition of tangent, right? And then the tangent is given by that is n pi over n. So n pi over n, that becomes n pi cosine. So this equals to that, and both have the same n pi coefficient, so n pi cancel. So sine R equals to cosine of b, which is sine pi for t minus of b. right? That's just a property of sine. Right? So you can see that R is equals to pi over 2 minus I sub b, so you have R plus I sub b equals to pi over 2 from this equation. Okay, so meaning in that when you have the boost angle, when you don't have when E is E prime, E double prime is 0, that this E prime is on the same direction as this K double prime. At least, I mean, on the same line. So it means that you're looking exactly, this is the refracted angle, you're looking at exactly the same direction as the E double prime. So for you, E double prime is always pointing at exactly your direction of observation. If you look at the refracted wave from this angle, you look at that this way, then the electric field is on this line, and the physics is that this electric field for this medium, this refracted wave, basically due to the oscillation of the charges for the upper medium or the refracted wave, what the refracted wave exists, and so this refracted wave will drive charges along this direction. But for you, the charges doesn't move because they're always on the same direction. So when we look at that, in chapter 9, when we talk about radiation, we show that the radiation, if you have an acceleration of charges or electric dipole along the same direction, the wave power is actually strongest at the perpendicular direction and zero along the direction of the movement of the charges. Okay, so that's all this oscillation along this line will not have power along this direction. So therefore, it's zero double prime is 0. Okay, so that's a physical explanation why you have this I that's Brewster angle, this I sub b will set this E0 double prime 0 because of this geometrical effect. And you can consider this the case 1 with the electrical perpendicular to that, then you always will not have this situation because the electric field will drive the charges going back and forth along the direction normal to the blackboard. So because of this, when you look at the refracted wave, and you're always looking at the charge movement always has a transverse motion. You always see the movement of the charges, and the radiation of the upper medium will not give you 0. So you always have radiation from the upper medium, so that will give you a non-zero refraction wave. Okay, so that is the difference between the two cases. Okay, so that's the first property. Okay.